So we are starting a new module in this class. The module is about large-scale machine learning. So what we will talk about is a class of methods for working with data that falls under the umbrella of machine learning, where the idea is that based on, we want to analyze the data, so that based on the features of the data, we want to predict certain properties of items or data points that we haven't yet seen or that we are going to see in the future. And the simplest method that we will talk about today is called nearest neighbor classifier. And based on this idea of nearest neighbor classifiers, we will then develop this into more complicated and more advanced machine learning models. The idea of machine learning, or what is known also as supervised learning, is that we would like to learn a function that is basically making predictions for us. So in an abstract way, we would like to estimate, based on the data, a function f of x, so that given x, we can predict y. Now, of course, the question is what is x and what is y? Most generally, there are kind of two separate things what y can represent. If y represents a real number, then this is what is known as regression, right? Based on some values of x, I want to predict a real number y. So for example, if I would want to, given someone's age and someone's ethnicity and so on, maybe I would want to predict their life expectancy, then this would be an example of a regression problem. However, y can also be a categorical variable, right? Which you can think of it as a binary variable or something like that, right? This predicting a categorical variable is known as a problem of classification, right? So for example, one case of classification would be that I give you a document or an email, and I want to ask you, is this spammy email or not, right? So given a document, you want to decide, return a binary variable, 0 or 1, where 0 means not spam and 1 means, yes, this is spam, let's discard this email. Of course, you can also predict kind of more complex objects. For example, you can sometimes, y could be a ranking, an ordering of things, or it could be, for example, if you are working with sentences, y could be a whole parse tree. But what we will focus on in our lecture is mostly on classification. So basically, given a set of x's, decide what is the label, the binary label of every x. And why do we call this whole thing supervised learning is because we think of our data as labeled. We are thinking that we are getting a set of many pairs x and y, where x is the data that we are getting, and y is the variable or the class that we want to predict. So we can think of S as a vector of binary, categorical, or real valued features, and y as the class, let's say +1, -1, or a real number if we are working with regression. And if we think about this case, basically we can think of x as a set of features representing our data point, and y is the property of the data point we want to predict. So if I want to predict spam, then for example x could be a set of words in the email, and y is a binary variable that tells us whether that email is spam or not. If I would want to, for example, model human diseases, x could be a set of symptoms or set of characteristics of a patient, and y could be whether that patient suffers from that disease or not. So this is the first idea, the idea of having a set of features and then having the dependent variable that we want to predict based on that set of features using our function f. Another important idea is that we will think of our data in some sense as coming as this big matrix, right? Where we can take our feature vectors and stack them together in a matrix, and then we can think of our dependent variables y, so the class values that we aim to predict, as a long thin vector. And of course, what we can also do then is to say, based on this, what we will call training data, we want to estimate our function f, so that whenever we observe some new unseen data x prime, we will be able to predict what are the associated class values with this unseen data, right? So the idea is that we will want to learn our function f based on the training data set that is labeled in a sense that we have both x's and y's. And then in the future, our hope is that we will get this new data set, this we call it a testing data set, where we only know x's, and from x's we will try to predict these y's. So we will always kind of think about the training stage of our algorithm and then the testing or the application stage of our algorithm. So in this module, we will talk about several different machine learning methods where we'll be kind of focusing on large-scale data. In particular, we will talk today about k nearest neighbor, which is something that a method in a class of instance-based learning. And then we will also talk about support vector machines and decision trees. And kind of the main question when working with machine learning methods is how do we efficiently train or build a model based on the data. So in a sense, the main question that arises in machine learning is how do I find this function f that takes the input features and predicts the class variable, right? So learning or estimating this function f is the hardest part of machine learning. So an example of instance-based learning, the idea here is that we want to use existing instances or existing data points to make predictions about unknown or unlabeled data points. So the example of such a method is called nearest neighbor, right? Where the idea is that we take all our training data, all our XY pairs, let's say in memory or on the disk, and then whenever a new query example, let's call it Q, comes, we find other examples X prime that are similar to it, and then based on the labels of those examples, we also predict the value Y star for the given query point Q. So what is interesting about nearest neighbor is that it works both for regression and classification. And if we think about recommender systems, in particular collaborative filtering is an example of a nearest neighbor classifier, right? There the idea was that when a user comes, we find k most similar users to our given query user Q. Then we look at what these other k most similar users, what are the movies they liked, and based on the movies these other users liked, we are making a recommendation to our query user Q. So this is exactly an example of nearest neighbor, where a query arrives, we find nearest data points. Based on the labels of the nearest data points, we kind of try to combine those labels to talk about the label of the query point. The simplest of all nearest neighbor classifiers is what is called a one nearest neighbor classifier, right? Where the idea is that whenever we want to make decide on a label of a given data point, we simply find the point most similar to it and use that label as a prediction. So in particular, when we want to implement a nearest neighbor classifier, there are several things we have to decide on. First is we have to decide on a distance metric, right? How do we measure similarities or distances between data points? So for example, in the case I will show you here is, let's assume we are using Euclidean distance. Then another thing we have to decide is how many neighbors are we looking at? Are we looking at one nearest neighbor, 5 nearest neighbors? How many nearest points do we want to examine? So in our case, let's look at one nearest neighbor. Another important thing is how are we weighing these different neighbors that we are combining together, right? So in this case that I'll show you, we won't worry about this just yet. And then another important question is, how do I then take all these nearest neighbors and combine their values into a single point that I will use as prediction? And in our case, because we are just using one nearest neighbor, all we have to do is just predict the same output as is the value of the nearest neighbor. For example, now if I show you how this works, here I have a simple two-dimensional data set where I can think of the x-axis as the input feature and the y-axis is the value I would like to predict. And blue points are my data points, and the black line shows the output of a one nearest neighbor classifier. You basically see that for around every point, we exactly just predict the value of that point. And then if our data set is noisy, our prediction jumps around quite a lot. If our data set is nice and smooth, we are basically predicting this almost like a step function. So this seems to be working quite well in this simple example, but we are seeing what the method is suffering from. It is making lots of very spiky or sharp decisions because we are only looking at the one nearest neighbor. So we want to generalize this and maybe try to kind of use more nearest neighbors to average better. So let's look at how that works, right? So if we want to generalize now our method and call it a k nearest neighbor, then now the idea is we will still use the Euclidean distance. Now how many neighbors will we look at? We will look at k, where k is some number chosen by the user. And then how do we combine the labels of all the k neighbors into one label? For example, right now, let's just say that our output will be the average of the classes of the k nearest neighbors. So very simply, for example, here is our data sets from the previous slide. We are using here k equals 9, which means we are averaging together the y value of the 9 nearest points to our query point. And given the blue data, this is the predicted value that we would make. For example, notice that now our predicted function, our function f of x in some sense, if you like, is much smoother than what it was before. While nearest neighbor is a very simple method, one thing that we haven't yet discussed is actually how do we go and find nearest neighbors. So the task here is basically given a set of points in some space. So this is basically our data set. Our goal is to find another set of points that are close to our query point Q. And there are two types of queries we may want to ask. One type of query is to say, give me nearest k points to our point Q. And another way to ask a query would be the range search, where we would say, give me all the points that are inside some distance of Q. In both of these cases, a naive solution would require a linear pass over the data, so it would take linear time, but we already know how to do this better. For example, using locality-sensitive hashing, we could find nearest neighbors in near constant time. So that would be a good way how to really make nearest neighbor classifiers scale to large-scale data.